Hello everyone, we are back here with another question. This question number 3 from JEE Advanced 2023, paper number 1. We have been having a series of elaborate solutions for these JEE Advanced papers. Now we have done 2 questions as of now. We are going to the question number 3. This question was based on some reactions which were covering different chapters. You can see here in fact this time they had mixed basically an organic question many of the chapters while framing the questions. So they have framed this question covering the concepts from the alkene, alcohol, carboxylic acid, alkyl halide, cyanide, that's nitrogen containing compounds, carboxylic acid, EAS reaction, and even in carboxylic acid there was a reaction as Volhard Zelinsky HVZ reaction. So many concepts put together in a single question basically. And because they had kept 17 questions, they wanted to be it much more lengthier, although not very much difficult reactions, not very confusing reactions, not very much time-taking reactions in the way that you have to think upon a lot. You have to think about many reactions to get the correct answers. So we are going for paper number 1. This was held on June 4, 2023. We are having elaborated solutions, and this is what I'm claiming, that people are doing the video solutions, but they are not giving enough time to all the aspects possibly some students might be thinking of. So my attempt is, when I'm doing these questions, that you should be getting detailed insight of every single question, every single option, what was present in the question paper. So this was section 1, one or more than one correct. This was third question. Here we go. This question was about starting from styrene. Styrene we know as the vinyl benzene. So benzene basically containing one C double bond C. With that we are doing some reaction. That is the first step of reaction is we are reacting with this B2H6, that is diborane, and this diborane is now further being modified by reaction. Like this is hydroboration, oxidation, basically all these steps put together. And the product P, which is formed as alcohol, this product P was reacted with 3 different sequence of reactions. 2 sequence actually we'll say. The first one was the CrO3 and H2SO4, that's oxidation. Second one was this is some HVZ reaction where the carboxylic acid form was supposed to be oxidized, and then we have had this reaction with water, that is basically to convert things back into the carboxylic acid. Now this compound P, which was formed as an alcohol, that was reacted with SOCl2, that is your cyanide, Darzen synthesis we say, that gave chloride. This compound was reacted with NaCN, that gave us some cyanide. Cyanide was hydrolyzed and heated. So that is supposed to be giving us some corresponding carboxylic acid as the product. That CN is also converting to carboxylic acid over here. This carboxylic acid and that carboxylic acid are going to have some different relationship. I expected they could have asked the question on that as well. And then this R, another acid which was found, was reacted with the concentrated sulfuric acid. We have had a brief discussion about this particular step in the last question, question number 2, in the end, when they have tried that sulfuric acid hot. They did not give that concentrated sulfuric acid over there. That was another situation. So we have ruled out this kind of possibility over there. Here that possibility is happening, that this is going to give us some acylium carbocation, which is giving you intramolecular EAS. We are going further in all these all these questions, all these reactions one by one. So whatever they have asked here, this was very much straightforward, that what are these major products Q, R, and S. We have to identify what is this compound Q, what is this compound R, and then what is this S, that we had to figure it out. So here we go. We'll be taking these questions one by one, and I have tried keeping all the products which are being formed in this reaction sequence in one place. So as we do in quantum, we do superimposition. If you remember Schrodinger's cat, then we say this is in the superposition states of being dead and alive at the same time. I try to do the same thing with my compound. So all the compounds, starting from the beginning, from the styrene, if I tried pasting all those compounds one over another, this is what finally looked like. May not be making a lot of sense. Once we are done with all these steps, you'll see what was all this. And I have Literally, I have copy and pasted all the compound over here in the same thing. This is how it looked like. Okay, here we go one by one, all the questions. So this is our reaction sequence. We have seen that in the question already. Without much delay, I'm going to the detailed reactions. So that was first reaction sequence where we are getting P and Q being formed. In between, there was no such compound named. I have named that compound as Q over here. So that is your what we call as the HBO. We call this reaction as hydroboration oxidation. We'll be splitting all these steps one by one. So first of all, we'll be talking about the step number 1, which is going to be the hydroboration, and then so this reaction we are going to talk in detail. Then we'll be going further one by one. Then we'll be taking this step. Then we're taking this step in the third slide. Going here, this is the fourth step we have called this as HBO, which stands for hydroboration oxidation reaction. And if alkene undergoes hydroboration oxidation, we are getting the product as alcohol. Here is the product number P, which we have got as the alcohol in the final. In the basically these two steps, what were there? That is B2H6 in presence of THF and hydrogen peroxide in presence of sodium hydroxide. So this reaction, when we say HBO, which basically stands for hydroboration oxidation, this is having two steps. This first step, step number 1, is considered as hydroboration. The second step is considered as oxidation. This reaction has regiochemistry. Regiochemistry means when parts are being, like when two different atoms or two different groups are being added across the double bond, where H goes and where OH goes, that we consider as regiochemistry. Second thing is stereochemistry. Stereochemistry means when this H and OH are entering into a molecule, then where they are ending up, like they are ending up into from the same side of the face of the alkene, or they can be from the opposite side, or they can be from the both sides. That is considered as stereochemistry. In this question, stereochemistry was not asked, so we are skipping the stereochemistry. We are just talking about the regiochemistry. So this is anti-Markovnikov of addition of H and OH. So what we are saying is, if this was a case like this is the double bond, then Markovnikov would have given us OH over here and H over here. Markovnikov stated that the more electronegative part adds to that carbon where we are having less number of hydrogen. This would have been the Markovnikov product. Now, because here we are saying this is anti-Markovnikov, so in the anti-Markovnikov, now if we are doing hydration, we are expecting that OH will be coming over here and hydrogen will be coming over here. And because stereochemistry is not defined, then this bond could be written this particular way. That means stereochemistry not defined. Right? So this reaction HBO is anti-Markovnikov addition of H and OH. So if you see the initial and the final product, you will find that OH is appearing over here at the terminal carbon. H would have been here. We have not specified that where it is going. So actually this reaction, although is overall anti-Markovnikov, it is quite interesting, and it may be to some of students quite shocking that none of these steps in the HBO is anti-Markovnikov. Why I'm saying that, if you follow what Markovnikov rule, actually the original Markovnikov rule stated, it stated that when some HX is being added, then out of HX, the more negative part adds to that particular carbon which has less number of hydrogen atoms. Let us see here in this what we are having, this styrene. This carbon is having 1 hydrogen and this carbon is having 2 hydrogens. So if this B2H6 we can split into 2 times BH3, then we are having one as your hydrogen and another is your BH2. If you break these bonds H and BH2, what gets positive charge and what gets negative charge? The answer is hydrogen being more electronegative gets the negative charge, boron being less electronegative gets the positive charge. If someone of you is thinking this is not right, why hydrogen will get negative, why it should not get the positive charge, I would suggest if you look at that table of the electronegativity, you'll figure it out. Hydrogen is in fact more electronegative in comparison to boron. So if BH bond is polarized, hydrogen takes the negative charge, boron takes the positive charge. This is a little bit counterintuitive. If you have not been paying attention to the differences in electronegativity, you may have been thinking other way around. So once you are convinced that hydrogen is more electronegative than boron, now try applying Markovnikov rule over here. What would you say? You will now say the more electronegative part, which is that hydrogen of this BH2, this will be now adding to that carbon which is having less number of hydrogen over here, and this BH2 which was positively charged, this will be attaching to that carbon which is having more number of hydrogen. That was strictly a Markovnikov thing. So what we expected to be the intermediate between the reactants and products would be looking something like there will be one hydrogen and there will be one BH2. This is when B2H6 was being added. Although two more molecules of this styrene could be added to that two more BH bonds which are left. For making it relatively simple, we are not writing that. You might have probably seen that earlier somewhere else. So elaborating this first point, we are having here that step 1, the hydroboration. This is addition of H and BH2. This is strictly as per Markovnikov rules. There is nothing against Markovnikov over here. This is Markovnikov rule, hydroboration. We have realized over here already. So if you are now clear in this thought that more electronegative hydrogen is attaching to the middle carbon, that is a 2-degree carbon, and BH2 is attaching onto the terminal carbon. This was the step number 1, which was the hydroboration step. Now the second step over here is what we are calling as oxidation, and the result of this oxidation step is this electron deficient boron is being attacked by, in this H2O2 and NOH, we are having this hydroperoxide which is much better nucleophile that is attacking onto boron, and then there is a rearrangement involved. Although that rearrangement is driven by electrophilic boron, sometimes it is getting a negative charge, but that again becomes electrophilic only once it is losing one OH minus N from there. So in that electrophilic rearrangement associated with the boron is not changing the position of BH2 which was in the beginning, and after this oxidation step, this BH2 group is basically replaced by OH group in the final product. So this carbon where BH2 was present in the beginning, we are getting the OH group. The actual rearrangement of this HBO, how it happens, will be a little bit time taking. I would be dealing it in some different video, which will be on conceptual part that will be doing in the different channel, that is the chemistry, that is CHEM_MYSTERY. You can find the link of that channel into somewhere in the comment section or in the channel page description page somewhere. Okay, so this is the hydroboration oxidation. Oxidation steps requires one rearrangement, but rearrangement does not change the stereochemistry, implying that if H and BH2 in the beginning were present in syn fashion, they actually are present in syn fashion. Stereochemistry of this hydroboration oxidation is syn only. So H and OH in the final products are found to be attached from the syn side only. The idea is BH2 and OH do not attach from the different sides. To whichever side BH2 was attached from the same side, OH is also attached in the final product. Okay, so that was hydroboration oxidation, giving you the terminal alcohol in the end after this first step. Now we are going to the next step, which is going to be the oxidation, and this is because 1 degree alcohol. In the previous question, they had given us the same reagent, but we were having there 2 degree alcohol. So 2 degree alcohol was oxidized into ketone. No further oxidation was possible. Over here, we are having 1 degree alcohol. In the very first step, this will be oxidized into aldehyde. And because we know this is going to be a strong oxidant, we expect this strong oxidant will convert the aldehyde which could have been formed in the very first step into the corresponding carboxylic acid group. This is we have named as compound number X. So here are all those steps which we did. The important point once again, primary alcohol is undergoing oxidation into carboxylic acid. This is one of the very strong oxidizing agents because chromium over here is going to be in +6 oxidation state, and acidic medium chromium +6 is very strong oxidant. This is chromium +6 and this is going to be acidic medium. Okay. This is very strong oxidant, we know. So alcohol, 1 degree alcohol converts into carboxylic acid. 2 degree alcohol would have given us ketone. 3 degree alcohols cannot be oxidized if the temperature is not very high. They remain unaffected by the presence of CrO3 and H2SO4. And this reaction is actually kind of progressing by some mechanism, which is 1,2-dehydrogenation of the primary alcohols. We can think it this way. If this was some R CH2OH, like this is one hydrogen, this is oxygen, this is another hydrogen. So those radicals which can be coming from CrO3, they are going to abstract this hydrogen. So that abstraction of hydrogen, we are saying this is 1,2-dehydrogenation. This will be ultimately generating in something like this, that is aldehyde. This aldehyde in acidic medium undergoes the formation of the geminal diol very easily. So this geminal diol of this compound would be looking like there is one hydrogen, there is one OH, again there is one OH. Over here, if once again we are doing 1,2-dehydrogenation, again we are doing 1,2-dehydrogenation over here. So this is our carbon number 1, that is from hydrogen going from here. This is atom number 2 from here, oxygen, hydrogen is going. So if these two things are lost, what we will be getting is this is RC double bond O and OH. That is how carboxylic acid is being generated. Much detailed mechanism again we can be seeing somewhere in the videos in the chemistry channel, where we'll be doing in detail the oxidation reactions sometimes later down the line. Okay, so these were the steps in which the carboxylic acid is being produced. So basically aldehydes which are much more easily oxidized, which could have been generated by the oxidation in the first step of the primary alcohol, will be converting ultimately into the carboxylic acid group. That was the second step, that is we have written as the compound number compound number X, and this compound number X was actually reacted further with the chlorine and red phosphorus in presence of water. So that is what we are calling as HVZ reaction, which represents Volhard Zelinsky reaction. And that is alpha halogenation reaction, basically Volhard Zelinsky reaction. That is HVZ. So what happens in this HVZ when we are having alpha hydrogens present in the carboxylic acid? Usually we are doing this reaction in presence of bromine. Chlorine also gives fairly better results. And this is actually the kind of electrophilic substitution reaction. Why we are saying electrophilic substitution reaction? Because in this reaction sequence, what happens when first of all we are reacting this with chlorine or bromine in presence of red phosphorus, then we are getting some acid halide being generated. We need to compare basically these compounds. If you are having these kind of carboxylic acid groups, here there is very good resonance present because carbon oxygen bonds are not very much like carbon oxygen, their sizes are not very much different. But as you replace this oxygen group over here with some halogen, maybe it is your chlorine or it is bromine. So whatever halogen you take, that halogen will be going to give you the difference in the reactivity, because if you are say keeping here chlorine, the size of oxygen and size of chlorine are much more different. Here the resonance of the chlorine lone pair is not very much effective. That is going to give you poor resonance. Over here oxygen's resonance was very good, so this was not creating any problem. So this good resonance is not allowing enol formation. So if you say have here some CH2 group, something like this, and also if you have got say some R and some CH2 group over here, this compound will hardly give you any enol formation possible. This compound can give you significant enol formation because this hydrogen can undergo in conjugation, and this can be shifted over there. So when you are having acid chlorides, you have a possibility of this kind of enol formation, and these enols now can be attacking onto, because this is electron rich double bond, they can be attacking onto delta positively charged bromine or chlorine, whatever it would have been. That is how this electrophilic substitution is taking place. So hydrogen of the alpha carbon is being replaced as H plus. This will be forming one HBr. If it was chlorine, it will be forming HCl as the side product. So bromine, you realize here, will be giving you much better enolization in comparison to chlorine. So bromine have been traditionally used in this reaction. When we see HBr for the very first time, we talk about bromine. Red phosphorus and bromine are reacted. Chlorine can also be reacted. In fact, bromine is having both the pluses. Like one, it gives you better enolization. Secondly, it is better polarized, so the enol double bond can be attacking onto bromine in much easier way than it could attack the chlorine. So that was the idea why this halogenation is taking place. We understand the enol content of the carboxylic acid is very, very poor, as we have seen here, because this resonance is very good. This enolization is very, very poor. These two things are kind of in cross conjugation. Enolization is poor because resonance is better. And in the acid chloride, the situation has been completely different, because resonance is poor, enolization is becoming better, which is helping this HVZ reaction take place in presence of acid chlorides or acid bromides. We have now seen this is the enolization, which is making this reaction possible, and that final step in this reaction was the attack of enol, giving you the alpha halo acid. Actually, the initial compound which will be generated will be alpha halo acid halide. This water has been used because those acid halides which were supposed to be generating, they can be hydrolyzed very easily. You remember this thing, acid chloride, in fact acetyl chloride, if you take, they fume in presence of moisture as well. So this compounds will be converted back into the corresponding acids, and there will be formation of HCl. So this thing, this water has been taken to convert that group back into the corresponding acid. Alpha halogenation, this one which has taken place, it will remain, this halogen will remain, and one halogen which was present over here, that has been removed in the nucleophilic acyl substitution, and we are getting back the carboxylic acid group. That was the HVZ reaction, and this gives us the compound number Q, which is alpha halogenated alpha phenyl carboxylic acid. Right? Moving further to this reaction sequence where P was converted into R and then ultimately into S. Here two unknown compounds were there. We have named those compounds as Y and Z. So this is now the reaction sequence where the alcohols are being converted by SOCl2. This was your Darzen synthesis, which we have used as SNI. We have here, this is purely SN2 reaction where chloride is replaced by cyanide. We are getting some cyanide. Cyanides are being hydrolyzed to give you carboxylic acid as the final product, and this carboxylic acid is being converted in presence of concentrated sulfuric acid at some C double bond O plus. This is going to give you some intramolecular EAS reaction. ESI I can write. Sometimes we have written as SEI reaction for this particular case. So we are going to split all these different 4 steps one by one. Here we go. For the very first step, which was reaction with SOCl2, we have been calling this as Darzen's reaction, where any alcohol, you take 1 degree alcohol or 2 degree alcohol, which is reacted with the SOCl2, that is your thionyl chloride, and the thionyl chloride is a wonderful reagent in the sense when this is reacting with any of the alcohol, then this is giving all the side products which are volatile. So when SOCl2 was reacted with alcohol, we were getting the product RCl, HCl, which was volatile, would be collected very easily. SO2 is formed, which is also gas, can be collected very easily. So we are getting very clean product. This is one of the best methods of preparation of the RCl. Not just that pure products we are getting. Also, this reaction implies one extra advantage, which is retention of the configuration. So if you are starting with some compound which was having the halogen present at some chiral carbon, then the chiral nature of that compound will be retained in the final product without any risk of undergoing inversion in configuration or racemization of configuration. That's the beauty of this reaction, Darzen's reaction, use of SOCl2. We are calling this reaction as SNI, which stands for substitution nucleophilic intramolecular reaction. Here, when we are saying nucleophilic intramolecular, we mean to say the nucleophile is present in our leaving group itself within the reagent. So basically in this reaction, when your nucleophilic oxygen of alcohol is attacking SOCl2, the sulfur is going to be the electrophilic site in the beginning. That oxygen of the alcohol is nucleophilic, that is attacking. This generates something what we calling as chlorosulfide. This chlorosulfide is important key intermediate, which is basically giving you the breaking of some sulfur chlorine bond, and then there is a loss of SO2, and there is the generation of something what we are calling as intimate ion pair formation. As chlorine is leaving from this chlorosulfide, how chlorosulfides look like, I can write over here. This is R double bond O. Sulfur is being attacked. This is one double bond O. Sulfur has got one lone pair present as well, and this is another chlorine. This is what we are calling as a chlorosulfide is. In this chlorosulfide, what happens is sulfur is trying to pull electron from, basically the chlorine is trying to pull electron from sulfur. Sulfur tries to pull electron from the oxygen. So this bond is trying to shift that way, and this bond is trying to shift this way. When this is happening, we are having something we are calling as the intimate ion pair formation. So this R group is having O double bond S double bond O. R will get a positive charge and Cl over here will get a negative charge. Here is the catch, that from whichever side OH was supposed to be leaving, and where is the OH actually in the first place in this reaction? Hydrogen has been lost from here in the previous step. So this was the side from which OH was leaving, from our substrate, from our alcohol. Now this was the side from which OH was leaving, and here only there is a chlorine present coming from SOCl2. From the same side, this chloride is attacking our R plus or whatever in the intimate ion pair this group is present. So the side from which OH was supposed to be leaving, from the same side chloride is attacking. This is why we are having a retention in configuration observed in this reaction, where we are reacting it with SOCl2. Also, it is important to note, if here we are not using pyridine, this is completely SNI. If we are using pyridine, there was inversion in configuration. Also, there is one modification. If we are using some cyclic ether as well apart from pyridine, then there was twice the SNI, which is twice the SN2 reaction, which is going to be same as a retention in the configuration. Those details of the reactions again we can be taking later in some other video when we'll be doing the reaction mechanisms, or maybe in the preparation of the alkyl halides. That all depends how you like all this discussion. If we feel there is a requirement, I can be doing more videos as per a requirement of the viewers. Moving on, we have said here alcohols are reacting with SOCl2 in an SNI fashion. This is giving us alkyl halide. That as the final product, that is the final situation. We have written this compound as Y is being formed in this final sequence. Now this Y is being attacked in the next step with the sodium cyanide. That is a purely SN2 reaction, because sodium cyanide, the cyanide is actually very strong nucleophile, and carbon being sp hybridized in cyanide, there is not very much risk of elimination with the 1-degree alkyl halide, or even 2-degree can be quite safely used in this SN2 fashion, and we can be getting the alkyl cyanide formed. Here it is important to note that if you are using the ionic cyanide like Na plus Cn minus is present, or K plus and Cn minus are present, in these cases carbon is the nucleophilic atom which is attacking the alkyl halide. Although use of different solvents can change the relative nucleophilicity, so protic solvent will be disfavoring the attack of the carbon. So somewhere we have used ethanolic KCN to imply that we are trying to do SN2 reaction in much better fashion rather than SN2 reaction in the sense with respect to carbon as a nucleophile, because if you are using much protic solvents, then the negatively charged carbon can be much more easily solvated, and that can be preventing that easier SN2 reaction possibly from taking place. If this was some covalent cyanide like AgCN, then because carbon's lone pair is not readily available, in case of AgCN, because this bond is not completely broken, then this nitrogen is becoming more nucleophilic. That was the case. That is going to give you, like if you are reacting this compound with Rx, that was known to give us RNC. So isocyanates were resulting when we are using covalent cyanides. When we are using ionic cyanides, carbon being nucleophilic, we are supposed to be getting the cyanides as the product, or the nitriles sometimes say these compounds as. So that is your compound number Z. Now going further, we have written this next reaction where this chloride, the cyanide was undergoing hydrolysis, and this is at high temperature. So we have seen this discussion already, how cyanides are hydrolyzed in presence of acidic medium, and this is going to give you the carboxylic acid group and ammonium ion. This discussion of the protonation of the nitrogen attack of water and then the subsequent attack we have seen already. So once again, if you want to see this, it's C triple bond N. This is protonated nitrogen, water attacking over here, this bond being broken. So we are getting COH, double bond NH. Again, same thing happens, nitrogen gets protonated like this, and then again water molecule attacks like this bond again being broken. So we are getting something like this, what we have written over here. This is basically, there is one OH group here, there is one NH2 group here, and there is one OH group here. This is very much unstable compound, and here there are different possibilities. We could have got OH as a good leaving group because you are having OH in excess in reaction medium. We are basically having a lot of water molecules present, and acidic medium can be preferably protonating NH2. So NH3 plus can be leaving very easily. We are getting now the carboxylic acid group, and NH3 is going as being protonated ultimately in the reaction medium, will be converting into ammonium ion. So this is your final product, which is going to be formed as, this is alpha carbon, this is beta carbon, beta-phenyl carboxylic acid is resulting after this step of the hydrolysis of the cyanides. Later on in the last step, last sequence of reaction, what we are doing, this concentrated sulfuric acid, this is the thing what we have done in the question number 2, and we have told because there are no concentrated sulfuric acid being taken, we can be ruling out that possibility. Here that thing is actually going to happen. You have taken here concentrated sulfuric acid, this can generate over here the acyl carbocation. So what we are expecting in this case, we should be getting something like C double bond O plus. And now because of these alpha hydrogens, we have got good hyperconjugation, so these two positions are activated. These positions can attack onto this positive charge, and we can have this kind of 5-membered ring closure possible in the final product. So this acyl carbocation, basically we are saying this is intramolecular EAS reaction. Sometimes we are writing this as substitution electrophilic internal reaction, just like S and I was there. This is happening here, and we are getting this 5-membered ring with the fused oxygen present, like fused 5-membered ring with respect to one benzene ring. So we are getting here some cyclic ketone as the 5-membered ring. That is the final product which we have written as S. So these are all the reaction sequences. Now we'll be putting these things back into picture. So we'll be seeing what was right and what was wrong. So these are once again all the different products what we have seen in the previous reaction sequences, and we had to identify. So we can see from this all reaction sequence what was Q, what was R, and what was S. They had asked us to identify. This was your compound number Q, which was the product of the HVZ reaction, that is alpha-chloro-carboxylic acid, that matches into the product number A and B. C and D can be ruled out from here. You can see that very clearly. And then compound number R is going to be beta-phenyl carboxylic acid, because there is one extra cyanide group coming from the NaCN. So in the compound number R, there would be 2 extra carbon than the benzene and the carboxylic acid group. So R is ruled out over here. That is the correct product of the R. And once again, if you see the compound number S, there is a 5-membered ring fused with this benzene ring, which is giving you compound number S having one ketonic group present. So this is the thing. This was supposed to be our correct answer, and answer which we are finding given by the answer key as per JEE Advanced was also the same. So that was a pretty long discussion, once again, as expected, as you might have anticipated. I hope this was well up to your expectation. If you feel so, please consider liking and subscribing, and keep me motivated so that I could do more such videos. Hopefully we'll meet again in the next video. Thank you. Bye-bye. Take care.